Howdy, Lyndon.
Hey, Doug.
How things going for you since I got you here by yourself right now?
Busier than I expected it to be week 2, honestly.
What are you taking right now?
This strength of materials and circuits too.
Yeah.
I'm not very good at circuits.
Strength of materials.
Mhm.
I'm going to take that, or at least teach it to myself.
Mhm.
I think I understand a lot of it already, but I've never formally looked at it.
Mhm.
I'd like to teach it, then I know I would learn it. Yes. Skater math. Let's see. Seems like we need a blank piece of paper first. And it further seems like we need to have graph paper to write on. All right, we're all in the house. Let's do it. Goodbye, radio. Kills me to turn you off. Toto. Any Toto fans out there from the 80s? Well, let's see. So, what we are looking at in this section, and by the way, I'd like to update you about the syllabus. If you notice, this is the end of week 2. And next week, we really have a couple of projects and a test in the middle. You may notice on your syllabus that I set the test up to be on Wednesday, kind of between the 2 classes, so that we don't kind of waste one of our class days. This will give us more time to kind of play around and get our mind around things. So I want to teach you something today, and then Tuesday next week, we'll do a project that will help you, in a sense, get ready for the test and / maybe talk about the test a little bit too. And then you'll take the test sometime on Wednesday, kind of between the 2 classes, and then we're going to play around with another project on Thursday, kind of before we start the next topic. So note that in the syllabus. And if you look at your note sheet, yesterday we looked at the fact for kind of, let's see, what section would that be yesterday? Then the 13.4 section, kind of the 13.4 section. We looked at linear motion. And by the way, again, just a side note, I don't know if this is super important, but in chapter 12, we studied kinematics. Kinematics is just what engineers call the study of motion, kind of the classic equations that we've been working with as far as motion is concerned. But we didn't consider the causes. Kinetics is actually considering the causes of that motion. Come on, man. Focus. Learn how to spell. Causes of the motion. And yesterday's or Tuesday's 2 problems, we saw 2 causes. One was the force I put on the kayak causing it to slide across the grass. And the second one was gravity, the skier. But in both cases, those things were sliding along linearly. So these 2 causes might be some kind of a pull or external force, something happening to it. But the largest one, and the most interesting one, I think, is gravity is kind of our second force. So now we're looking at what causes that gravity. Well, today in 13.5, I believe, as far as the assignments are concerned, Yes, 13.5. We are looking at also kinetics, motion, except for this time we're going to look at motion that's curved. So that would be like a car traveling around a curve. I mean, you think about how limiting straight line motion is. Even the skier we looked at the other day, from the side view was sliding straight down a line. But if you ever skied before, you tend to be like swoosh, swoosh, swoosh. You're going left and right. So you're, very seldom going straight. So car might be going straight for a while. That's great, rolling down a hill. But if you're in that, like on a mountain bike, you might be turning left and right. And so we want to talk about curved. And notice that's a really broad category. And what we looked at the other day, we already started to look at with tangential and normal acceleration and so forth, is that we can always consider this as a circle, which is amazing considering if you ski down a hill, you're not skiing on circles. But we can always at least consider it for us as a circle, but that's of course at an instant in time. So just because it's fun, this is one of the things you do in kayaking all the time. So just as an illustration, the river is kind of flowing this way, and you are, one of the funnest parts about kayaking is if this is a rock, then there is an eddy behind the rock, which sort of just means a calm spot behind the rock where you can hang out. So one of the cool things about kayaking is you could just cruise over there behind that rock and just hang out in the middle of a rapid. And so one of the other fun things to do is you're sitting here in this current, and then you say, all right, just to kind of screw around and have fun, I'm going to peel out of this eddy and get into the current. And you're actually traveling on a circle when you do that. It's neat. If you'd ever like to see this sometime, I go to Gold Hill all the time and screw around in a rapid there called Nugget that you can see really easy. It's kind of a big, fun class 4, and you can see what kayaking looks like and get motivated and come learn how to do it with me sometime. Super fun. If you're so inclined. But anyway, you actually in books will talk about this. Like you travel in a circle, so you'll turn out of that kayak or turn out of that eddy, and then you'll peel out into the current, and then you'll actually go straight, maybe say from here to here. You'll go straight for a while, and then you'll actually peel into this current. And notice those are kind of two different radiuses. The first radius I came out on is wider, but what you're really trying to do, like if you can do that smoothly, that's kind of what makes kayaking sort of fun. And so that's kind of what I mean here. Like there's straight line motion, there's curved motion. And what I hope you understand from the other day is just that when you're on a curve, things are much more interesting. If you're at this point right here, tangent to whatever circle you happen to be on, the velocity will always be going in that direction. That's the direction you're aiming. Your velocity will always be tangent to the curve, as well as your tangential acceleration. And that's you either paddling faster or paddling slower. So you're changing your speed. You have a speed and you might be changing your speed. But then, based on where the center of this circle might be, you also have your arrows pointing at the center, and that's your normal acceleration. That's the fact that you're changing direction. And so, in other words, you have to have a normal acceleration to change directions. Does it make sense that on this straight path down here, your normal acceleration is 0, meaning you are not changing directions? So all you have in this section is, if you're sort of sitting right here, all you have is a velocity and well, it'd be kind of weird to call it tangential acceleration because it's not tangent to anything. But in a sense, at any moment, you might decide to turn, right? And suddenly it will become tangential. But that's kind of the idea here. Interesting. So, particularly interesting in this kind of an environment. So I just want to make sure you have a good feel for that. Well, what are we talking about in this section? Well, in this section, we're talking about how the sum of the forces, well, is not equal to 0 because I want to, I'm actually going to get moving. That's what we did with the skier the other day. Well, this is no different. In other words, I want, if you look at your note sheet, I want the sum of the forces in the tangential direction. So the forces, again, this is what's causing you to move. Does it make sense in the case of this kayaking example that there'd be two things causing me to move? One of them would be me paddling with my arms. The other would be the current hitting me. So this is exactly what I was describing earlier, external forces like the river or the paddle, a couple external forces. And then of course it's gravity that's actually causing the river to go. Does that make sense? In other words, the river is getting its force on me based on gravity. And so it's just kind of cool to sort of see this in action in a little bit more of a real environment. Well, the sum of the forces is equal to mass times acceleration, but because we've limited this to tangential forces, then we've got to limit it to tangential accelerations. So this allows us to kind of turn and sort of figure out what's going on. Figure out our motion. We're going to be moving. We're going to have acceleration. I'm going to be constantly speeding up and slowing down in the river, right? Based on what's happening here. One of the super interesting things, especially about Nugget Rapid, is there's an eddy at the top of that I catch. And when you sit here, you're obviously just sitting still, but the river is just flying by here. And so you peel out of this eddy, and as soon as the river kind of catches the side of your boat, you just rip downstream. And so I'm accelerating. Again, that's tangential acceleration. I'm going from no speed at all to super fast, ripping downstream based on that change. And that's what this is referring to is, yeah, you're going to have a large tangential acceleration here, a large change of speed. And of course, dependent on what the mass is as well. And that's going to be as a result of all those forces like me paddling and me, the river, if you will. So again, just to increase your intuition, my speed will change. And these forces like the river or my paddle strokes, that's what's going to change this. But secondly, that's also true for your normal. Whole nother set of formulas based on normal. And again, what we're talking about here is changes in direction change. This is a direction change. Why do I feel the need to switch colors? Seems like it just stands out. This is a direction change. Normal forces. Where's a normal force? Where would the normal forces be? In this picture up here. Well, they're in that normal direction. They're going the same direction as AN. Can you appreciate that when you're coming out from behind this rock right here, that the river hitting your boat kind of to the side, when it hits the front of your boat, that is going to turn your boat. So that is causing you to change direction. As soon as the front half of my boat gets hit by the front of the water, then it's going to get pushed downstream. And so that force is actually going to cause both a change of speed as I get out there, but it's also going to try to change my direction, right? And then of course I can do the same thing with my paddle strokes. I'm pulling really hard with my right hand, which will actually turn my boat to the left. And so there's direction, a whole bunch of direction forces. Again, this is just like last time, this is caused by the river hitting me and turning my boat. And it's also caused by what paddle strokes I might make that kind of control that. And of course, my goal is to stay in control, not die, like not go someplace I don't want to go. Or maybe in this example, just to screw around, like I want to get from one place to another. Watching a kayaker go from one rock to another rock and how controlled they are kind of is a super good gauge as to how good they are at it. Are they able to predict with their practice, not even with all this mathematical knowledge we're adding to this, but just based on their intuition and their skill and their practice time out there? Do they have a really good feel for exactly how the river is going to change their direction so that they aren't knocked off balance and flailing and so forth? Or is what's happening to them expected, if you will? You could tell a lot by somebody just making that move that I described right there. In the end, kayakers sort of call this collectively an S turn, obviously because it's kind of shaped like an S. But do you see how it's like a collection of circles and straight lines? And realistically, there aren't any straight lines. Really, you actually peel out of one eddy and you just curve in a circle. That's kind of what ends up happening. And so you're actually on different circles constantly. And so I'm very interested that you see, that the radiuses of those circles are changing all the time. This is a circle right here too. It just has a, kind of a really large radius, if you will. So anyway, hope that gives you kind of some intuition. And then there is like a cousin to this that we seldom need, because this right here is kind of all we need. It's all we need for kind of a 2D problem. And notice in my kayak example, we're looking down at it from the air. That's all we need is 2 dimensions. We've kind of got our X going this way and our Y going that way. And so it's kind of all we need. But there's also the sum of the forces in B, which need to be equal to 0. And this, in a sense, is kind of the vertical plane. Now, would you also agree, though, that, I am actually changing? In my case, in the case of a kayak, I'm progressing downhill. So this is a 3D sport. I am actually either going up in elevation or going down in elevation. But typically, this is equal to 0 as long as we're in 2D. So you'll see that in your note sheet. But basically, that B stands for you don't need to know this, but that B stands for binormal. And it just means kind of perpendicular to the plane. So in other words, there are no forces. The sum of the forces perpendicular to the plane that would cause you to lift up in the air or go down are 0, at least if we're going to keep this simple. Of course, like I said, there is such a thing as 3D motion, and that's get more complicated. But let's go see if we can apply this to an example. Do you have any questions about that? Do you feel like you're kind of tracking with this? And again, kinetics. We're studying kinetics here, which is all of the forces that cause all of this. So let's do an example. So ignoring everything else, here's a skater in a half pipe. And of course, we're going to oversimplify this by making the half pipe some equation that we recognize, in this case, like a parabola. But it could be a circle. A half pipe is typically a circle. Or as I've said in the past, you could actually take your own measurements and find some equation that modeled, just a skate park example. And maybe that shape is, elliptical, or perhaps it's exponential or something. It could be any equation and you could make it up yourself. But of course, what's causing this skater to go down the hill in the half pipe, and notice right now the skater's at the point 12.3, what's causing him to go downhill is gravity. So just like yesterday. But you see the problem from yesterday? Yesterday, we were on a flat plane like this, and we might say that angle is like 32 degrees. What's the problem with applying that same logic here today?
You're not going straight down.
Yeah, does it make sense? Like as soon as you get down here, now all of a sudden the angle's different. So the angle's changing all the time. On the ski slope, it stayed the same angle the whole time, but now we're changing angles all the time. And so that's why we're creating a new axis now. We don't have an axis that's just an XY. We have this movable axis. Like when you're up here perpendicular to that, that's kind of the normal axis, and that's the tangential axis. So there's our axis. But what happens when you're over here? Well, notice the tangential axis is still to the center. I'm sorry, that's the normal axis. The normal axis is always pointing to the inner part of the circle. It's pointing to the center of the circle. Now the tangential axis is, well, that way. Well, how do we know it's that way? Well, if the skater is coming out of the bottom as the picture would show, perhaps it's that way. Does that make sense? Maybe he's still, and you probably understand that when he gets to the bottom, he's going as fast as he could go, and he actually begins to slow down. Does it make sense his tangential acceleration up there would be negative? He'd be slowing down thanks to gravity, and at some point up here, he'd actually come to a stop. So do you see what I mean? Like the axis here is kind of cool because it just depends whatever point you're at. Then we set up our axis for it with a normal and a tangential axis, and that is kind of our XY axis. It's just not X and Y. So it actually changes all the time. That's what's beautiful and amazing about this. And so we're going to look at this as a circle, really, even if it's a parabola or an exponential or some free form concrete that a mason made for a skate park. So, anywho, what's this problem asking? The 48 kilogram skater rolls down the parabolic slope. Oh, look, we're given an equation for it.
Zoom audio.
Kind of a sterile. A sterile parabola equation. Fine, that's great. And his velocity is 8 meters a second at x equals 12 meters. So that's where we are. So we're sitting there at 12 meters. And we know his, again, doesn't that feel very contrived? Like, how do you know it's 8 meters a second? That doesn't make a whole lot of sense. But remember, and we'll get to this in the next question, but does it make sense if you started, up here, there's your skateboard, and then you dropped in, then the fact that your gravity pulled on you all the way down to that point, then you would know your speed. In other words, that's just like yesterday, in the sense that we started at the top of the hill and then the skier slid down the hill. And then that's why he ended up with a certain speed at the end of it. Well, that's kind of true here too. I'm just oversimplifying it to begin with and saying, let's pretend we, don't know how he got there, whatever. So then the problem says, awesome, then find the normal force. And I said NS for N of skater. The pipe exerts on him. And I said, what's the normal and tangential components of his acceleration at that point? So all I know is just where he is and his initial velocity. And so, what's your thoughts? Do you read that and kind of immediately find yourself thinking, gosh, I don't know what I would do? One of the things, I didn't say this in this problem, but friction is a gigantic problem when you're curved like this. So every question you see in your book will sterilely do what we're also going to do here, which is solve this friction with a frictionless. The other word you'll sometimes see in your assignments is the word smooth. You're going down a smooth parabola. Well, that's not a very good word choice because smooth just means not bumpy, but that's code in your book for no friction. Maybe we'll have a chance to talk about that, but friction, applying friction in this case would be very difficult. If this was a box sliding down it, to say there's no friction is almost idiotic. Of course there's friction, but at least with a skater, no friction is at least approximation because they have bearings that are all greased and it's not going to slow them down that much. So I do need to know that. Anyway, well, I don't know. What do you do? So we're sitting here at this certain speed. Does it make sense, because I know where I am, does it make sense you just like the skier on the hill yesterday or Tuesday, you have gravity pulling on you here, and that's a very important force, right? But what angle is it pulling at? What angle is the gravity pulling at you at the point 12.3? Can you find that? Like yesterday, it was given 75 degrees, but how can we find it here? Do we even need to know it? What are your thoughts on that? I'm going to draw a free body diagram while you were thinking about that. So I'm at the point 12.3, and I've got a velocity of 8 meters a second, and it's tangent to the curve. So there's my velocity. But then that's also the same direction as your acceleration tangent. And then perpendicular to that would be your acceleration normal. What else is happening to you at that point right there? Would you agree that gravity is always pulling straight down? Maybe I'll even say the force due to gravity. I could say gravity, force due to gravity, doesn't matter. But that's what's so weird about this, is that force will always be straight down, not perpendicular to the ramp or anything like that, just straight down. What else is happening to this? Is there any other things going on? Is there any other things I need to consider? What's happening here? I'm missing one. Who knows what it is? It was something we had to add for the skier Tuesday as well.
Normal force?
Yeah. The normal force of the skater. Notice that's going the same direction as A of N is. And as a matter of fact, I could have even drawn it up there if I wanted to. So that normal force, the pipe is pushing on the skater. And if he wasn't, he'd be falling straight down. So that's kind of a free body diagram, but it actually doesn't have forces on it. Does it make sense if I put forces, then AN and AT and 8, those aren't forces? So if I actually made a free body diagram kind of for real, in a sense, that was more just like, what am I trying to figure out? Free body diagram, but I'm just going to kind of show the forces on it. Then it's going to be the same thing. I'm just going to copy it since I can. Copy, paste. But I think just to make it look good, I'll redraw it like this. Like this would be the normal of the skater, and I'd have gravity pulling down, and this would be gone because it's not a force. Really, that's all I have right there. Do you agree with that, or is anything missing? So this is really just a picture of kind of what's happening. Well, think about this. This is, in a sense, no different than what happened with the skier now, because I'm looking at this little instant in time right here. Does it make sense, just like we did the other day when we had the skier and we chose to turn the ground level, and we said gravity was kind of pulling in this direction? Does it make sense the other day we said, well, we need to convert part of that to kind of the force in the X direction and the other part of it to the force in Y direction? In other words, we had to split it into its two axis components, because the force of X was causing us to slide down the hill, and the force of Y is actually trying to get us to sink into the hill, which, as we noted, has an effect on gravity, right? Or has effect on friction. If you're pushing down into the hill, the harder you push, the more friction you're going to have, and it's not going to want to slide. And so the same thing is true here. We've got to split that force of gravity up to kind of break into its tangential and normal components. We need the tangential and normal components. because that's all we have. That's my point. Is in these, in this world, the only directions we really can work with are normal and tangential, our axis. We've got to switch everything to be in those directions if we're to use the formulas that we have about forces, which were again normal and tangential. So on a curve, you don't have a choice. You got to consider a circle, and therefore you got to be at a certain point because you're at a different circle any place, depending on where you are. So let's see, let's just figure a couple things out here. So then the force of gravity. Well, how am I supposed to figure out? I want to hear an answer from you on this. How am I supposed to figure out what components of that, and I'll add them in here. What components of that are, this would be the force of gravity in the normal direction, or the opposite of normal direction, I guess you could say. And then running across this direction would be the force of gravity in the tangential direction. How am I supposed to get those when I don't know an angle?
We could start by finding the derivative at that point.
Exactly. And that's why it's essential to either have an equation to produce the angle that we need or to go out there and physically measure it. There's no reason you couldn't put a level on the ground out there and actually figure out what the angle is right there. But we're going to need to know what angle we're at, because that's going to tell us, notice these two forces, what part of our force of gravity is going into the ground, and then what part of it is actually getting us to speed up downstream. So notice that force of gravity tangential is actually causing our speed to increase. So yeah, that's exactly right. So let's take a look at that. So actually, let's just go over here and kind of ask the question theta. And Landon couldn't have said it any clearer. If I take the derivative of this thing, y prime, notice that's a nice, neat equation. 2 times an eighth is a quarter, so that's 0.25x. And maybe I'll write it as 1/4 x. And the derivative of 2.25x is 2.25. So that's 2 1/4, which is 9/4. I don't know why I'm writing it in fractions. So there's my first derivative. Notice it's a recipe that calls for x. Well, I know x. And again, this is why it's so important to know where you are, because the angle depends on where you are. So notice it makes sense why the slope that you're at depends on where you are. So this is saying, yeah, it depends on x. Okay, so y prime of 12 would be 1/4 of 12 is 3. 3 minus 2 1/4 is 0.75, I think. Okay. So I know the slope. What do I do to get from slope to angle? We did some of this last term, but I think this is just such a cool application to calculus that I want to give you another fresh shot to understand it. I'm all ears, tell me.
Just draw a little triangle.
Yeah, you don't have to have this memorized. If the rise over the run is 0.75, then wouldn't the rise be 0.75 and the run be 1? Or you could rewrite it as 3/4. So this is the angle. Notice that's a tangent problem. That's where tangent got its name. That's why somebody decided to call it tangent. You didn't know that in Math 112, but you do now, because tangent is slope. So the tangent of the angle is going to be equal to the slope. So if I go inverse tangent with my calculator in degree mode, I get about 36.9 degrees. But you got to be a little careful. Do you know where to put that? Do you know what angle in my picture over here is 36.9 degrees?
From horizontal to tangent.
That's exactly right. It's always going to be from horizontal to the tangent line that we're talking about. And notice in a sense, like, dang, that's not in my picture, but notice I know that this angle is 90 degrees. So that means, what is that? 36.9 plus what is 90? that would be what, 53.1. So this angle here would be 53.1. But then isn't this angle also 90? Isn't this angle also 90 right here? So if this angle is 50.1, then that would actually cause this angle also to be theta. In other words, both of those angles are 36.9. Doesn't matter which one you use, but I think that last one that I drew, theta right there, probably is the most helpful, because isn't that actually in this green and purple right triangle that we're considering right here? So now that I know that, I can actually see what forces I have. Well, first of all, let's figure out what the force of gravity actually is. Force equals mass times acceleration. It's one of our classic ones. Gravity has an acceleration of, let's see, am I working in feet or meters? I'm in meters per second, so everything is meters. So my acceleration of gravity is 9.81 meters per second squared. I was told how much I weighed. It was 48 kilograms. By the way, what's the 48 kilograms a measurement of here in this picture?
Mass.
Say it again.
Mass.
Yeah, what is it? The mass of what?
The rider and board.
The rider and the board. That's exactly right. It's like the whole system. It's the rider plus the board. In my case, it's the kayak plus the paddler plus his paddle plus whatever else is inside his boat. It's the whole deal. So anyway, collectively, we're told that's 48. But notice the skateboard's left off that. I don't mean this to be complicated. So cool. I multiply that out. What do I get? I get 470.9. So 470.9. Again, newtons. Very annoying that newtons and normal are in these problems. And so that's a number that I need. Okay, well, now I'm ready to use that right triangle that I have up here. I'm ready to use that right triangle to figure out what I need. And so I can say then a few things. I can say that the sine of theta, which for us is 36.9, would equal the opposite of that. Oh, that's the force of gravity tangent divided by the hypotenuse, which is force of gravity. So the force of gravity tangential divided by the force of gravity. And we know those now. We figured those out. The force of gravity is 470.9. And so now I can solve for the force of gravity, its tangential component. Beautiful. I do that. I get 282.7. So force of gravity tangential is approximately 282.7. Again, please interrupt if something is bothering you about this. Again, I'm trying to model. I don't really know what to do here. I'm not doing this as step 1, step 2, step 3. I'm just figuring out things that I can think to figure out. And I'm making a note of them by kind of drawing a box around them saying, oh, I might need that later. But I might be figuring out some things I don't need later. Similarly, the cosine of 36.9 would equal the force of gravity normal. And so similarly, if I switch that out for 470.9, I end up with the force of gravity in the normal direction being approximately 376.6 newtons. So remember those formulas for the force tangential and the force normal. I kind of understand all the forces. They're in this picture now. So since the skater is not, well, let's just start into it. So now I'm thinking about those formulas that we made for ourselves, or that we looked at, that the sum of the forces, I don't know which one to do first, normal. equals mass times normal acceleration. Sum of the forces normal. Well, look at my sheet. Don't I have two forces that are normal? I have the normal force of the pipe pushing up on the skier, and then I have the normal force of gravity pulling down. Again, this isn't so obvious. Which one is positive? Which one is negative? How do you know what positive and negative is here? Positive is always pointing toward the center of the circle. That's positive. Positive for y is always in the direction that you're traveling. So notice that's what's weird about this. It's not left and right anymore. It's entirely based on the direction of travel, and that's not obvious at all. So from this picture then, I've got normal force of the skater, or normal force of the path or the pipe or whatever. And then I've got the force of gravity kind of pulling down. Those are the two forces. So I've got normal force of the skater going positively minus the force of gravity normal, which is negative. And we said a second ago that that was actually 376.6. That's all the forces. Do you see what I hope you've seen earlier in this class last term, that if you don't get your free body diagram drawn so that you actually have all the forces that you need, you're in deep trouble. And secondly, that you need the forces all to be reconciled into their normal and tangential components. That's the only axes we have to work with here. It's not X and Y anymore. So that's all the forces I have, and that's equal to mass times the acceleration normal. Well, I know my mass, that was 48. That's not a very happy equation because I don't know. I got two unknowns. What are your thoughts on that? Two unknowns. Don't like that equation. Doesn't mean it's wrong. Well, I don't know. Let's just put it off for now. So I'm not sure. Let's go on and do the sum of the forces tangential. What forces are tangential? Well, again, thanks to the free body diagram, we broke that up, and there's only one. The force of gravity tangential. That's the only thing going in the tangential direction. And we know what that number was. It was 282.7 newtons. And we know the mass. And let's see, do we know the acceleration tangential? Well, we know the mass is 48. This equation, one unknown. Happy. I can solve for acceleration tangent now. So obviously I'm just dividing both sides by 48. And if I do that, I get acceleration tangential is about 5.9 meters per second squared. That feels like a, I don't remember what this question was asking, but that feels like something that's kind of more important. So I found that. That's cool. But that doesn't really help me up here, right? Like it didn't tell me anything. It didn't tell me anything that kind of helps me go back to that fifth equation to solve anything. Who can tell me how are we going to get out of this mess? Like, how am I going to make any more progress? I kind of feel like I'm stuck now.
Could we possibly look at like the total forces on it? And then knowing one of the accelerations, try to work our way backwards the other one, or
Yeah, what about all of the forces? Well, don't we know all of the forces? Like, didn't we already break our free body diagram has the forces on them. We were forced to kind of describe those according to normals and tangentials, not according to kind of a normal XY axis. So in a sense, we already have. Hmm. Well, don't forget what we've learned before. So this is kind of the two things we're studying for this first midterm, chapter 12, chapter 13. But these two equations are what we need to consider. This is a formula that needs to kind of stand out to us that, hey, that's how you get acceleration normal. You need to know the velocity and you need to know the radius of the circle that you're traveling on at that moment. Again, even though this is a parabola, for a brief instant in time, we're traveling along a circle. And I know my velocity, we were told that was 8 from nowhere, but I don't know my radius. Well, that's what this other formula is. It tells you your radius based on the derivative of the equation. So we can actually see what radius or circle we're traveling on thanks to calculus. And so that's our n here. Those formulas still work. That's the same set of formulas that we used before. Just like yesterday or Tuesday, we used these formulas for straight line, linear motion. Now we're in curve motion. So we have a couple of formulas for that as well. So that's my out here, which again, I don't think is obvious. Neither do you, since none of you said anything about it. So let's use those. 7. The second derivative of this, remember the first derivative, I'm assuming you're looking at that formula, but the first derivative was 1/4 x minus 9/4. So the second derivative then would just be 1/4. So maybe I'll just write that down first. Since the first derivative was equal to 1/4 x minus 9/4, that means the second derivative is just 1/4. And so we need to know all of those for that formula. So we already figured out earlier that y prime at 12 was 0.75. So isn't the rho formula, rho looking something like that, wasn't equal to 1 plus the derivative squared, all raised to the 1.5 power divided by the second derivative. The second derivative evaluated at 12. Well, in our case, it doesn't matter where you are. The second derivative is always 1/4. Like, it doesn't have an x, so it doesn't make any difference where you are. Second derivative on every place on this half pipe is 1/4. So if I punch that mess into my calculator, I actually get the radius of the circle I'm on, which punching in is approximately 7.81 meters. That's kind of cool. So I know my radius, which means now I can punch out what is the acceleration normal, because it is equal to the velocity squared divided by rho. And we know now that rho is 7.81. And we were given our velocity of 8. And so if I square 8 divided by 7.81, 7.81 is notice fairly close to 8. So I don't get that different of an answer. I get approximately 8.2. Again, 8.2 meters per second squared of desire to change directions. So my speed change, notice it was positive. My speed change, of course, is positive because I'm going down the ramp, and so gravity is going to be speeding me up. But my direction change is bigger than that. It's like profound. It's really pushing me to change directions. Little side note, just kind of a side note. There used to be this jump over at Mount Bachelor when I was first skiing called the compression jump. And it was really cool because you'd come ripping off this road and you just fly off of this jump and you'd kind of go, kind of land down here someplace. But then once you landed, you're just skiing along like this. And then when you got to the bottom, there was a super quick change of direction, really sharp, like a small radius circle at the bottom. And what would happen when your ski kind of turned and started going up the hill is it would like knock you back on your back, like you'd fall over backwards because the normal acceleration, I didn't understand it at the time, but because the normal acceleration is pushing so hard on you, that's what that 8.2 is representing. It's pushing so hard on you to change directions that you end up smashing against the ground. Again, I said the common name for this is centripetal acceleration. That's why when you turn your car really sharp, you sort of fly into the door, so to speak, because you don't want to change directions. You just want to keep traveling that way. But then the snow says, no, you're going to change directions. And so naturally you kind of smash into the door. So the point is now I can sort of revisit question. I can revisit 5. And I can now find the normal of the snow pushing against me. So 376.6 equals 48 times now the acceleration normal, which I'll write here and then replace with 8.2. And so finally I can find the normal of the snow pushing against me. And that is a surprisingly large number, which is 770 newtons. Now, again, I don't even know if I answered the question. I just figured stuff out here. Find the normal force S the pipe exerts on him. Yeah, we just did that. And the normal and tangential components of his acceleration. So yeah, we found all of those things. So in the end, yeah, that was tangential, that was normal. So in a sense, I should box that in my way of thinking, since that was an answer I needed and then this final answer. So cool. One of the things I'd like you to understand, though, is remember how big gravity was in this problem? Remember, the entirety of gravity was 470. That's how hard gravity is pulling on you. How in the world can the snow be pushing back at 770, nearly double? Like, how come the snow is pushing back with 300 newtons more of force? How can the snow be pushing so hard on you? Doesn't that seem like this answer must be wrong? Does anybody have any intuitive thoughts on that?
Well, depending on the state of the snow, like relatively compressed snow, it's really strong. And if you're on skis, even less compressed snow, it's like the force is spread over such a larger area compared to the usual footprint of just standing on snow.
Let's consider that, what Landon just said. Does it make sense if you're standing here and you're just not moving? It's like flat snow, and gravity was pushing down with, say, let's just keep it in simple language here and say it's like 120 pounds because that's how much you weigh. Does it make sense the normal force of the snow then is also going to be 120 pounds, assuming you're not flying up in the air or sinking into the snow? Isn't that what would happen? In other words, the snow is required to push back at 120 in order for you to stay still, and it will. And as Landon pointed out, your skis tend to disperse that. But if you were in soft snow and you didn't have skis on, it would not be able to push at 120 and you'd sink for a while until it kind of compressed enough that it was able to push back. So that's my whole point is You know, if this was suddenly 240 pounds, does it make sense that can't really be the case? Because isn't that going to make you fly up in the air? The answer is yeah, it is. Well, if you fly up in the air, that's exactly what's happening when you turn a corner. In other words, if you came down a slope here and you're turning really sharply like this, you're getting the 120 just because the snow is not letting you sink. But then you're getting this normal force changing your direction. And so you're getting really gravity plus your weight. Does that make sense? You're going to get is that right? No, gravity and weight are the same thing. You're getting your weight, which is effectively gravity, plus you're getting the change of direction. In other words, that's what normal acceleration really is. You're getting a force in the normal direction, your change of direction. So that's why it's so much bigger, because not only is it holding you up, you're also being pushed on to change direction. So at this location in the bottom of the pipe, you're getting down here where the circle is pretty tight, in which case it's pushing on you a lot to kind of go, you know, along the black line, if you will, instead of along the purple line, the tangential line. It's changing your direction. So that's why it's so much bigger than just the force of gravity. And really, the force of gravity is the force of gravity normal. So it's kind of like this force. I mean, it really is double that force. Is your intuition growing there a little bit? Do you kind of see why that would be so much bigger? Early on, for instance, I was tempted to say, hey, look, if this is pushing down at force of gravity, which we said was 282, no, that was normal, 376. This was 376. I was very tempted to immediately say, oh, well, then this will also be 376, because wouldn't those be equal? The answer is yes, they would if you were actually traveling on a straight line. But we're not. We're being pushed on. So that is not the same. So all I'm saying is, you know, grow your intuition a little bit and kind of expect that to happen. That's pretty complicated, right? There's a lot going on there. You got to know calculus. Study this example carefully so that you agree with it, not just because, you know, I did it that way and I'm the teacher, but so that you can kind of reason your way through it yourself. And notice I solved this in a totally different order. If I had just read this problem and say, find the normal force S, okay, I'm going to go find it. Like, I don't know if I can't, I don't think I could do it. The steps, if you need them to follow, is number one, uno, very importante. Number one, get a free body diagram, which, by the way, implies forces. Really, this is not over here on the left, a free body diagram. Get a free body diagram, and then just start figuring stuff out. Don't even read the question. Just start figuring out what you can figure out. I probably didn't do this in the best order that it could be done in, but who cares? So this is what's so awesome, because what we're really getting at here is these are all the forces on the skater that actually cause the motion to happen. Notice there's no external forces here. There's nobody pushing or pulling on this person. It's just them sitting on a skateboard cruising down the hill based on gravity. And so we would need to understand all of the forces involved. And so, you know, the important equations here that are sort of brand new for us are these 2, 5, and 6. I've got to break it into a normal and a tangential coordinate system at the particular point I'm at, and all of my forces have to be broken into those components. And then that'll allow me to know my, and this is going to be always the questions you're ultimately asked to figure out is, what is the normal acceleration and what's the tangential acceleration? Because of course those questions are, are you speeding up or slowing down, and how hard are you being asked to change directions? And that 8.2 we got down here for the normal acceleration is a pretty big change of direction. It's pushing pretty hard on me to change directions. And so those are the things I need to understand. Like in order to understand that motion, what's going to happen next? Well, if I know my tangential acceleration, then I could say, well, I was going 8, but 1 second later, thanks to this calculation, I'm apparently going to be going 13.9. So I'm changing speeds. And then great, you're changing speeds, you're going faster. Okay, that's really cool. Where are you going? This number right here tells us, hey, I'm being asked to change directions. So that tells me how it's kind of hard I'm being pushed in a different direction. Does it make sense? Armed with all of these numbers, I have a sense of what's happening to me at that moment. Again, though, I think the thing that's really interesting about this is, do you agree that half a second later you have to do this all over again because you're at a totally different point with a totally different slope, and that's going to change all of your accelerations? So in my mind, a good question here would be to say, okay, well, let's do this for 1 second. So now we're in a new location. So, where would we be? And then recalculate everything. Now what's happening to you and so forth. And you would notice that you're, again, to grow your intuition, you would notice that this acceleration is going to go down because you're getting yourself onto flatter and flatter terrain. So gravity is not speeding you up as much. So if I went 1 second later, that might drop to 4.3 meters per second squared. Who can tell me what's going to happen to this number as you progress deeper into the pipe? Is that number going to go up or down based on this picture? In there, you are getting to a tighter circle, a smaller circle, which means that radius right there is going to get smaller, right? Which means the overall acceleration normal is going to get bigger. In other words, you're in a tighter circle, so that means you're being pushed on harder. There's more curvature down there. So our tangential acceleration is going to get smaller as I move to, say, this location. But because I'm on a smaller circle, my normal acceleration is actually going to increase. And so although it's kind of cool that we made all these calculations, does it make sense they're only good for 0.1 seconds and then you got to do it all over again? Interesting. Anything you want to ask me about that? I can't think of anything else I want to say to you, so. So what I want to look at with the rest of our time, and I hope we get done with this, is kind of the skier jump project. And actually this isn't the jump project, this is actually an introduction to it, but let's just play around with this a little bit. So notice this is very similar. It's another parabolic ramp, but notice in this case, the skier starts from rest. So this is a skier this time. Notice it's ridiculous to say without friction here. Do you agree with that? Skiers have friction. But friction is very hard to work with because every point you're at, the force changes. In the skier the other day on the flat ground, that friction force stayed the same the whole time. But here the friction changes depending on where you are. So you'd actually have to recalculate it 100 times to actually get how much friction force is on you. But this is more realistic than the previous question because this time we're not just magically sitting there at some point with 8 meters a second of speed. This time we don't know what speed we're at. It's coming because we just started from the top of this and sort of dropped over the edge. So for you skiers, think of this as a half pipe and you're sort of like right here, about ready to drop off of it. And so as soon as you tip over the edge, as soon as you give up the normal force of the snow pushing on you that keeps you from falling, as soon as you get to the edge, no more normal force, gravity starts to make you fall. So metric again, at the point 0.18, without friction down the ramp, we have the equation. But notice this equation only exists from 0 to 12, which means this really is a jump. And can you picture in this situation that the skier is not going to kind of come down the ramp and then make it to here and kind of go doom, 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 to a stop? They're going to have enough speed to make it back to here and then take off from there and fly through the air in the shape of a parabola. So this is just the same as what I did with you guys with the skier the other day, except the skier went down a flat ramp and then went off a jump. This time they're going down a curved ramp and then hitting a jump. So the question is, what will happen? Well, I'm giving you a hint here just to save us some trouble. Remember that equation that I've kind of hinted at a few times, wrote it down once, but we've never bothered to use it. This is a place that will save us a bunch of time. So what we're going to do is travel down. We're interested at the point where x is equal to 3. And so I say, okay, cool. X is 3. That puts me right here. And we could go on and say, okay, great. Now that you're at 3, then what happens later on? But I want to see, can you do some of this yourself? So notice, and let's just do this together. Notice in this equation up here, your initial velocity, which is 0. So v squared equals initial velocity squared, but your initial velocity, because we started at rest, is nothing, plus 2 times, and notice this says vertical here. It's the vertical change of distance. Remember how we break our all of our calculations into horizontal and vertical. And because this is frictionless, then we can say we're not losing anything. So this is like free falling. In other words, this is no different than free falling from a height of 18. Well, notice the coordinates of this point right here is 3, 8. So we're basically falling from 18 to 8. We're falling 10 feet or 10 meters. And we know the acceleration vertically, it's in this case 9.81 meters per second squared. And the distance, the difference between the starting height and the finish height, the starting height was 18. The initial height is, no, the initial height is 18. The finish height is 8. So again, that's a difference of 10. Technically, this acceleration is negative. So since 8 minus 18 is negative 10, then I'd be multiplying by negative 9.81. I'm going to get that. Let's see, what is that equal to? The velocity squared then, did I already calc this just to save us some time? The velocity squared is approximately 200. And then I would square root it. I think I'm just going to calc this really quick. 2 times 9.8. I didn't have that written down. So 196.2. And then if I square root that, I get 14.00. Actually, I think I made a mistake here. Is this really at the point, I'm looking at my notes all of a sudden and realizing, is this really at the point 8? I thought it was just looking at it, but maybe it isn't. Let's go figure it out. What's this point really at? So if I say, what is y evaluated at 3? So in other words, 0.2 times 3 squared minus 4 times 3 plus 18. Do I actually get 8? I should get something really close to 8, but what do I really get? Yeah, I don't. I get 7.8. So that means this is actually 7.8 minus 18. Yeah, that's where I got the 200. So v squared is 200 point something. 200.124. And if I take the square root of that, I get 14.15. So So that's kind of cool that you can work your way down here. So I'm just going to call this point A. So that means point A is equal to 3 and 7.8, just to have that written down. And then I can say here that the velocity at A is 14.15 meters per second. That seems important. So can you add that to your knowledge from what we just did a minute ago? Isn't that kind of cool? If it's frictionless, that I could use that equation to see what speed was actually generated. So now I'm not just being given 8. Go ahead, Daniel.
That was me actually. Am I crazy, or does this graph not actually match the equation?
That's a good question.
Because I just in my head I was thinking at x equals 10, it probably should be below. Like that's 20 minus 40 plus 18. Is that -2?
It may not match the graph, but I thought it did. I'm going to stick it in real quick just to see, because it'd be nice if it did. If it doesn't, I probably changed it sometime in my teaching without actually changing the graph, which is dumb. Zoom 6.
Yeah, at 10 it goes down to -2. And
Yeah, you're right. Yep.
This is the same y-intercept though.
Yeah, it doesn't match the graph. You're right. So it's actually a good thing I plugged that in. So it matches it okay here, but
I've got the graph to match the equation to match the graph. It's just 0.25x instead of 0.2x. I'm pretty sure.
0.25.
Mhm.
Yeah, that's unfortunate. That means I must have changed it and not insert 5. I'm just checking out what you got. I'm sort of surprised I didn't choose a point that was exact. That's kind of what's bothering me. Trace 3. Yeah, I mean, you're right. That's certainly closer. I mean, we'll go ahead and go with what I got, but notice in this problem, we're not going to continue to the jump, which is actually a good thing to note, because if we are considering this as ground, then we don't want the graph going into ground. Fortunately, we're just saying what's happening at all those, at 3. And so it kind of won't hurt that it doesn't match, but I'm glad you pointed that out, because that's not good. So I'm sort of here at x equals 3. Cool. Well, notice I know the velocity now. That's kind of cool. I can at least type that in. So what I want to do is just give you a second now. Can you do what we just did then? It's no different from here. The main thing is to, if you will, establish yourself here and say, okay, cool. So there's my tangential acceleration. Perpendicular to that would be my normal acceleration. Those are 90 degrees. So that's kind of what's happening. That's the axis I have to establish. Notice those are again drawn in the positive directions, positive direction of travel for tangential acceleration, toward the center of the circle for normal acceleration. Remember, your first order of business for this would be to draw your free body diagram, because you got to get all the forces involved. And I'm going to just remind us of that. I'm probably going to pick on you here, pick on random people. And I kind of would prefer you get it wrong, just so that we learn something from it. So notice these sort of 5 answers I'm asking for are in no particular order. I just kind of wrote them all down there. NR stands for the normal force of the ramp. This is the ski ramp. So Evald, what are you working? What did you work on first? Maybe you're still working on that. Maybe you've moved on, but what did you do first?
I mean, before you said about free body diagram, I was working on radius of a circle.
That's a great idea because radius is dependent on the parabola's equations, right? Like the derivative and the second derivative. So notice that's a good place to start because you know that you have the equation. I like it.
I got 563.03 meters
For what?
for radius.
That's too big.
Too big?
We're going to run out of time, so I'm going to catch up to you guys and start playing around with this too. But let's see what happens for that. That's a good place to start. So let's see, what are my derivatives? I'll go back to the free body diagram in a minute. So to get rho, so I've got to have my first derivative. The derivative of that would be 0.4x minus 4. And so y prime evaluated at 3, x is 3, since that's where I am, is 1.2 minus 4, which is negative. Better write that down somewhere. 1.2 minus 4. 1.2 minus 4, that'd be negative 2.8. You should not be surprised by that's negative. Isn't that a negative slope? And also 2.8 is pretty steep. And so you should be able to go, oh yeah, that is a big number for a slope and it's negative. That makes sense to me. And then the second derivative of that is just always 0.4. So now I have everything I need. I can say that rho is equal to 1 plus the derivative squared, all of that raised to the 1.5 power, all of that divided by the second derivative. If you throw all of that mess in there, I guess I'm going to do it with you because I have what I consider the right answer to be written down, but I don't see my work. Oh, there it is. Yeah, you should get 65.71.
Okay, yeah, that's what I just got. And I have to go to work, so I will see you next week.
Yeah, and so, on my sheet, I said that our first project, the skier jump project, I'm going to go post that in projects right after class, but it's very closely related to this. And so that is your first project. It is due. It is something you want to work on because it's just this, except for 2 different answers, so you can compare them. And anyway, I'll post that. So notice that shows up on your syllabus. That's the first one you're going to do. So let me, so yeah, awesome. We'll see. I'll bust through this really quickly. Well, now that I know that, does it make sense you could find A of n? Because A of n is velocity squared divided by rho. And since I know my velocity at A is 14.15, I'm just kind of using things that I know. If I divide those two, 14.1 squared divided, I end up with 3.05 meters per second squared. And so that's a cool answer. That's one of the things I needed to know. So that's cool. Let's see, what else could I figure out now?
Theta is just going to be the tangent inverse of negative 2.8, which is negative 70.346 degrees.
Nice job. The inverse tangent of negative 2.8. I agree with you. Negative 70.3 degrees. Again, notice that fits the picture here because if I'm here, wait a minute, does it fit the picture? If I'm here, does it fit the picture? Yeah, is it negative that direction? So you're down, not up. So then that looks about right, doesn't it? So you went in the negative direction clockwise. And so that does look, close to 90. So notice again, that's cool. It actually looks correct. Nice job. I only have 2 things left I have to figure out. And for these, I am now, for the first time, actually going to need the free body diagram because this is where I got to get all the forces involved. And so again, just so that I can kind of get you guys out of here on time. Do you understand that I would have gravity going in this direction, straight down, but more importantly, I've got the normal force of the run pushing against me, and that's it for those 2 forces. But although this is the force due to gravity, I need to convert that into the force of gravity in the tangential direction. And right over here, which could also be looked at as right there, and the force of gravity in the normal direction. That's what I really need. So because that angle is 70.3, then I can figure those things out. So if I don't screw this up, I'll just write those in here since we're out of time. This one turns out to be 32.99. And the force of gravity tangential turns out to be 92.39. And of course, the force of gravity itself is going to be 10 kilograms times 9.81. So I'll just write that over here. The force of gravity itself is mass of 10 times 9.81. So that'd be 98.1. So 98.1 times the cosine of 70.3, 98.1 times the sine of 70.3. That's where those two numbers are coming from. So now I've got kind of now I've, if you will, got all of the forces broken into their components that I need. So it's kind of these that I'm actually going to pay attention to. In a sense, that's what I really want on that free body diagram. So now I'm in a spot to find the sum of all the forces and so forth. So let's see, last time I kind of got burned going for the normal first, but notice there's only one going tangential. So I'm going to start with that one. So to get the acceleration tangential, then I would have to be using the formula that said the force of tangential is equal to the mass times the acceleration tangential. So the force tangential we have in the same direction. Notice it's positive because it's going in the same direction as the skier, 92.39. We know the mass of the skier was 10. That means all I have to do is divide to get acceleration tangential. And of course, I expect this to be positive. 9.24 meters per second squared. I expect it to be positive because I'm going to be speeding up. Notice how much faster we're speeding up here than we were a minute ago. Now, a minute ago, we had a totally different weight of a skier, but this number is increasing pretty quickly here because we're on a pretty steep chunk of the slope. And so that's kind of cool. So 9.24. And then lastly, that normal force, which I'm going to get by coming up with the same sum of the forces, but this time normal mass times normal acceleration. So my normal forces, I've got two of them. I've got normal force R positive, 32.99 negative. Do you see that? Normal force positive minus 32.99 negative. There's two of them. I've got 10 for a mass, and I've got my acceleration normal, which I figured out earlier, fortunately, 3.05. So if I punch all of that in, I end up with the normal in the R direction of 63.5 newtons. And so that's how hard the hill is pushing on me again. Massively larger than the other forces involved. Well, some of the other forces involved. So cool. You guys okay? How's that feel? Do you feel like, yeah, two examples that were similar? I can do this.
Yeah, I kind of like this a little more than the last one because you actually just run through all of it.
Yeah, you sort of need to see it twice.
Yeah, I'm pretty solid on this now. A bit slower, but
Yeah.
It kind of cracks me up that we have to have such lightweight skiers to make the velocities not just be ridiculous.
Very good observation. You are in the loop enough to know that 10 kilograms doesn't weigh very much. Yeah, this is like,
wouldn't increasing the weight not affect the velocity? Because it also takes more force to get this amount of acceleration.
yeah, in the end, things don't. What that affects is the forces that are acting on it. But you're right, it's kind of the old Newtonian. I think it was Newton's experiment where he dropped a bowling ball out of the Tower of Pisa and some other, like a marble, and they landed at the same time. So they're being acted on the same. In the end, the weight of something cancels out. So yeah, that is an interesting observation. Okay, I'm going to post these notes, post that project for you guys right now, and I would recommend dinking with that, now, just while this stuff is fresh in your mind. And then we'll talk about that a little bit next time. Good to hang out with you guys.
All right, bye.
See you later.
See you, Doug.